Okay. So hello and welcome to Let's Sprinkle some perf matters on your ViewGroups. I am François Blavoet, so I work as an Android engineer at Deezer. In case you don't know Deezer, it's a music streaming application. Playing music is just a very small part of what we need to do in such an application, though. We have also fairly complex graphical requirements, such as displaying lyrics, complex layouts in order to display an album or a feed of recommendations, even Tinder-like view in order to choose your first artist on the albums during onboarding. So we have very complex graphical requirements. And during the past couple of months, I have been involved in a major rewrite of our UI stack. It has not just been a fresh coat of paint. We have also tried to improve our code base and rethink our UI code. For example, we have ditched ListView in favor of RecyclerView. If you are writing your UI, there is not really a lot of reason to keep ListView. If you need to be able to add items, remove them, do drag and drop, and so on, there is no question. We have also tried to focus on UI performances, and this talk comes from the lessons learned along the way. In particular, one of the most important and common bottleneck in UI code in the platform is often how layouting is performed. First, in order to create this new version, we tried to follow the material spec. One very important aspect of it is the idea that motion provide meaning. It is especially important on mobile, where we deliver a very tactile physical experience. If I take a Nexus phone and launch an app showcasing material, I can understand this concept. If I move my finger on the list, everything moves synchronously, and nothing blinks in or out of existence. However, if I take the very same application on a more modest smartphone, things don't go quite as well. This is a Galaxy Fame. It ships with 4.2 JBeans, so it can run most modern applications. It just can't run them very well. It's probably one of the worst devices that everyone is supporting right now. And honestly, you can't have good performances on this kind of device. It takes 5 minutes to boot, 5 more minutes to launch any application. It's just very bad. However, there are many devices on Android. There is a whole spectrum from flagship to low-end devices. And we have, for example, the Moto G. It is very popular, but it's not a flagship. It cannot handle everything you throw at it. In many situations, it will become very junky. And that's not something we are very satisfied with. You also have Android One phones, same thing. They are very popular. If you are targeting the third world, you are going to need to target these devices as well. And you can't just deliver this kind of experience. Nobody is going to be able to use it. So we are going to investigate how we can optimize an application for such a use case, or at least get as much performances as we can when necessary. First, let's define exactly what we want. So on Android, we try to render each frame in a 16 millisecond target. Why is that? Simply, if you divide 1 second in 16 millisecond segments, you get 60 frames. And 60 images, one after the other, are more than enough to trick the eye into thinking that it is a continuous movement. If we compare to other kinds of use cases, we have movies. Movies are not 60 FPS, they are 24. And in fact, the first movies were even at 16 frames per second. It's very low. The absolute limit you can live with on the human eye won't recognize as a series of images, but motion is usually around 20 frames per second. In fact, the only reason why movies have so low frame per second is because at the very beginning it was very costly to film something. So if we use less frames, it costs less. And it stays that way until now. We also have video games. Usually, in video games, we have 30, 60 frames per second. For some Western game, maybe double of that. But if you have 60 frames per second, you are able to deliver an instant response to any user input. If we miss a frame, it's not too bad. We are at 30 frames per second if we miss 1 frame over 2. Most users won't notice. If we miss more, 3, 5, 10 frames, we get junk. So what is junk? If I look at the dictionary, junk, the definition is just problematic blocking of a software application user interface due to slow operation. It's not really helpful. So in practice, junk is a choppy UI on the discontinuity of Notion. So each time we are not able to render at least 20 or 30 frames per second, the user will notice until it breaks the experience. And there is no use in implementing something as complex as a material application if the user only sees a slideshow. So what you are going to do is take a phone like a Moto G, an application that does not perform too well, and let's try to understand why and what we can do about it. The first tool we are going to use is Systrace. So it is bundled with Android Studio. It's a platform tool. All you have to do is launch the Python script. And let's say you scroll in a list, launch the script, and Systrace will capture everything that is going on in the system in all processes during 5 seconds. What you get is an HTML with this. So it's a bit intimidating, but in fact it's not really complex. It's just a lot of information. So if you look on the left, you've got the different threads going on. So in particular, you've got the UI thread. That's the one we are most interested in. On the Wonder thread, since I monitored the Marshmallow device, I not only have a UI thread, but also a Wonder thread in order to be a bit more performant. It does not really matter. If I only add one UI thread, I would get less performances, but the same logic from developer point of view. If I zoom in on a small part of this HTML frame, it becomes more understandable. So I've got this F symbol, and in this particular frame it is red. So it means that the system has tried to compute a frame, but was not able to do it in the 16 millisecond time frame. So the system had no choice but to do not display anything during that frame and wait for the next one. So again, if it is only one frame missed, they are worse thing, but if we are missing a lot of them, we have a problem. So fortunately, we don't have to look at the whole C-stress report during 4 hours and not all the problem we have. The tool itself gave some advice on what it can detect as the most problematic behavior during this 5-second time frame again. So, for example, we can have garbage collection. Java uses garbage collection, and mobile devices are extremely constrained. So a common issue is to allocate many objects, in particular in a critical part of the code, such draw method. Since they are run during each frame, if you allocate object, especially a large object in a draw frame, sooner or later you are going to have garbage collection issues. If I look at the advice, I got a couple of expensive bitmap plugins. It's not too bad. So if you have to handle bitmaps, do yourself a favor, use Glide or Picasso or whatever image loading library works for you. There are many options out there, and many of them are very well thought out, and does as good a job as it is possible to do with such large objects as bitmaps. Another advice I got is that I've got a couple of long draw operations. So again, 7 occurrences. It's not too bad. I've got maybe a couple of draw methods that are a bit too expensive. I've got some alpha problems. So that can be a bit more problematic. Alpha is always very tricky on mobile. Not all devices handle alpha layer very well. We have some tricky cases. For example, if you need to apply an alpha layer to a TextView, don't do it directly on the view object. Apply it on the paint, on the color that you gave to the TextView. That way, it will be optimized by the system as much as possible, instead of first computing the bitmap and then applying an alpha on it, which can be very, very slow. Finally, I've got a lot of occurrences of expansive measure layout paths. What does it mean? We've got, for each frame that we want to display, a call to perform traversal. So it's a system call that will traverse your whole UI, and if it is already measured and layouted, okay, everything is cached. So it will only call a draw for each view and send the result to the GPU. If you need to lay out some views, it will need to run measure and layout passes on each of your view groups. And this is where we can have often some issues on Android. So that's what we want to investigate. So we know that we have some expensive measure layout passes. We'll try to see exactly where. To do that, we use another tool. C-Trace only tells us that we have a layout problem, but does not really tell us where. So hierarchy viewer is a very good tool to identify which view exactly is creating an issue. Same thing, you launch it from the command line or from Android Studio, and you ask it to import your worldview hierarchy. And you get another bit intimidating graph. So in this tree, I've got my worldview, and I've got many objects to display. So the topmost object will be the decor view, the root of all the UI I want to display, and the rightmost ones are the final children, view children of what I want to display. What I can do next with this tool is simply ask it to profile how each part of the hierarchy is performing. I just have to click on a part of the hierarchy and on the profile node button. What it does is that for each node, we get 3 circles. So the first one corresponds to the measure path, the second one to the layout path, and the third one to quick display list, which roughly is the draw call. It is color-coded relative to the node you are analyzing, from green to yellow to red, and red are the slowest part of your hierarchy. That way, you can identify which items are causing you trouble. So typically, you are going to inspect a scrolling container, like a recycler view or a list view. It's the same principle. And not all objects are problematic. Only some view groups can hurt your performances, so you don't want to optimize everything. You want to use hierarchy viewer to pinpoint exactly which view group is too slow. Once it is done, we have no choice but to dive in the code in order to understand why it is slow. So, view group is a direct children of view. The only additional task is that a view group can have children views. Quite simple. And in order to display them, it needs to handle 2 methods. So first, measure each of its children, and secondly, to lay out them, so to tell to each child exactly where it is going to belong. Things get a bit more complicated if you look at a very rich view group like RelativeLayout. At its core, RelativeLayout collects a set of constraints on each of its children. For example, you will tell it that you want one view to be the topmost one, another one to be to the right of this first view, and so on. So you create a collection of constraints when you write an XML layout. And RelativeLayout will have to resolve these constraints. To do so, in its measure method, first, RelativeLayout need to ask each children, what are your constraints, and sort each children in order to determine which one depends on which other. When it is done, RelativeLayout can first apply all the horizontal constraints. So it will place, for example, the leftmost child first, then another one, and so on. When it is done, same thing, but for vertical constraints. When these 2 pieces are done, there are still some work to do. If you have asked in the XML to align to the baseline, same thing, RelativeLayout will need to compute that. If RelativeLayout is set to wrap content, it will need to compute that. In most cases, RelativeLayout does that very well. So I'm not saying you should avoid the RelativeLayout. It is a very good class and it is very useful. It performs way better than having, for example, 2 nested linear layouts. But when you start nesting a relative layout, so you have a relative layout with another relative layout as a child, with another relative layout as another child, well, each child needs to run this whole logic again. So the children applies the constraint, applies the remaining baseline wrapping, and so on, and very quickly it can kill your performances. When you are scrolling, you need to lay out each new children you add to the list. If you change the visibility of a part of an item of a list, for example, from visible to gone, same thing, relative layout needs to measure everything again, layout everything again. Again, it is costly. If you are scrolling, it can kill your scroll very easily. So what can we do? We could forget about ViewGroup and write a view that does everything. That's not a very good option. It's something that some applications do, and they are maybe right to do so because they have the means to write a lot of code. So Google Plus, for example, has a lot of very optimized UI code. But if you do this, you will have to yourself place every view without using ViewGroup logic. Draw the drawable yourself. If you want to apply a ripple, you need to do it yourself. So that's not a very good option in most cases. What we can do, though, is extend the ViewGroup ourselves. So if we look at the framework classes, they have a couple of priorities. First, be correct. If you ask an element to be on the left of another, the framework must give the correct layout. Secondly, they need to be versatile. Relative layout is a good example. You can display almost everything with this view. And only in a third place, you have performances. What we can do is forget about responding to every use cases on Earth and write something extremely specialized that will only lay out one very specific type of item. So we are going to take an example. So I took a view from our new Deezer application. It's not typically complex enough to get huge gains on custom ViewGroup logic, but it's the exact same logic whether you have three views in your hierarchy or 100. So I thought it would be better to simplify a little bit. If I look at how I would implement this with XML layouts, with the base framework classes, I would probably have something like this. So first, an image view for the cover with a relative layout as a parent. Then a linear layout in order to apply center gravity on two text views. Then two other image views for the buttons. And in some cases, with the hierarchy viewer, we can see that these base framework classes are not fast enough. So what we are going to do is forget about this XML layout, remove it entirely, and instead write a custom class. So let's call it album view, since we are going to display an album. We are going to put in this XML the constraint we want on the whole view group, as we would do with whole XML, but only for the parent. So I want its width to match the parent. I want it to have a fixed height, and I want some padding. Next up, I inflate this layout like I would do any other, and I feed it to my recycler view adapter. Let's dive in the code of this custom view. First, I need to implement a constructor. And in this constructor, I will call an init method. The goal of this method is to inflate the view I want as children of this view group. So here I want all my 5 items, so 3 my view and 2 text view. In this merge XML, I am not going to give any position specification, so no to left off. I will only give size recommendation, so I want, for example, to give 64 dp of 8 on width to my cover. I want the overflow button to have a ripple effect when I click on it. So I keep all the XML logic I would have in a framework class implementation. Because I don't want to lose that. I don't want to do that in code because separating code on the XML layout is very important in order to keep a maintainable layout. So I inflate this secondary layout and I extract each item as a field in this view group. Nothing too complicated, so I just have to do a find view by ID on each item. Next up, in view group, I need to declare which kind of layout params I want to give automatically to the children of the view group. The framework does not do it by default, but in almost all cases, you want to give it a margin layout params because you want to be able to give margins to your items. It's a very common requirement. So you just have to declare it in these 2 methods. Next up, well, we need to implement the measure logic ourselves. In fact, it's not too complicated. So the contract of the measure method is that for each child of the view group we want to display, we need to call measure child with margins. So it is a method of view group. So we don't even have to write it ourselves. This method will measure the child based on the width measure spec provided to the onMeasure method. And the framework calls it, so we don't have to compute anything. Next, we also have the width used. So the first item I am displaying, so I have not used anything. So width use and height use are still 0 at this moment. And now that I have called measure child with margins, I will just have to offset the width used with a measurement of this view. So I just have to write a little util method that will compute, quite simply, the measured width of the view and its margins. That way, we can item by item measure how many space we need. Next, I do the same logic for each child. So let's do the overflow, for example. The order does not really matter. So I just feed it the exact same parameter, except that the width will have increased. So by the way, in this example, we don't compute the height used, because if you look at the layout, it is a mostly horizontal one, and we don't care about the height measurement since we want a fixed height of 80 dp for the whole view. So we just have to call measure child with margin on each item of the view group. And when we have done it for everything, in order to fulfill the contract of view group, we need to call set measure dimension. So it is another util method of the platform. Its only goal is to declare to the layout system how much space do we need for this view. Again, view group provide utils method like resolve size that will take as a parameter the width we have used for all our items and the measure spec provided by the method onMeasure, and we'll compute the final measured dimension of the view group based on that. We don't have to implement anything fancy ourselves here. We just have to measure each children. So it is done. Now the measurement is okay. We just need to lay out each children. So it's just a bit more complicated, but it is mostly the same idea. So we are going to call for each child view.layout. So it's a method of view that just tell to each view exactly where it is going to go. So if we take the first view on the left, so it's the cover we want to display, just need to call layout view with the cover, the left position, which is just the padding left for the view group, the top position, just the padding top, the width, well, it's the width of the view, the height, same thing, it's just the height of the view, and the framework does the rest. Next, we need to update the space we have already consumed because we'll use it to offset each item as necessary. So let's continue to lay out our items. So next up, the overflow. This time, I want to put the overflow icon on the right, on the top most right position of the view, and centered vertically. So to do so, I call again layout view and provide the overflow field. The second parameter is the horizontal position of the view. So quite simply, it is right minus the left position provided by the onLayout method. So it corresponds to the position of the view group itself relative to its parent. So if we add the right position, subtract the left, we have the right corner of the view group. We subtract the padding, the size of the view. Okay, we have the left position. We want to center this view. Just have to do a simple subtraction and divide. It's nothing too complex. And again, we just give it the width and the height. And when we are done, we offset space consumed right variable in order to be able to simply offset the earth icon we want to display next. We do this for each view in the layout we want to display. And it's finished. We have the exact same layout we had when we did this with relative layout and linear layout. But it is entirely flat. We don't need any nested view group. The measure on layout code is as minimal as it can be. Can't really remove any code. It is just the minimal logic we can apply to get the position we need. So as far as measure on layout passes are concerned, we can't get any better. And in some cases, it's still not enough. Damn it. We have in fact, another big potential bottleneck in Android UI, it is TextView. So in almost all cases, again, TextView does exactly what you want from it and is not too costly. But sometimes you need to display many lines of text, or you need to compute many spans for the text, and it just takes a lot of time. And it's not always acceptable because in order to display, to make a layout pass, we need to call TextView on gigabit its text. And TextView we need to measure itself, so it can severely impact the layout pass performances. What can we do? We are going to take the album view class we have written earlier, and we are going to remove costly TextView. So again, it's a bit of an artificial example to do not write extremely long view group. So now I am going to draw the text myself. I will forget about TextView. So I want to draw in a view group. By default, view group declare that I will not draw. So you need to declare to the platform that you will not draw by returning false. Extremely logical. And next, in the onDraw method of the view group, you are going to get called. So you would not get a call in this onDraw method without overriding will not draw. In this onDraw method, the only thing I'm going to do, except calling the super, is calling a text layout helper class that I'm going to write and pass it the canvas in order to let it draw. So, how can we draw a text? It seems quite easy. It's just characters, but in fact, it is extremely complex. And in almost all cases, you don't want to call canvas.drawText yourself because you are going to lose right to left, spacing, automating line number handling. And it's not something that you want to write yourself. And in fact, if you look at TextView, it is a monster of a class. It's 10,000 lines, but it does not know anything about how to draw a text. It's entirely delegated to a child class, android.text.layout. There are two implementations of this class: boring layout, very original name, static layout, and dynamic layout. So dynamic layout is only used for edit text. So we don't really care about it right now. Did we say boring? So the first implementation of text.layout is boring layout. So it's a class that has been added in the first version of Android. And well, it is quite boring. So in order to use it, you need to call an util method. So again, it's provided by the platform with the text you want to display, the paint you want to use, and ask it, is it boring? For the platform, boring means a simple draw operation. So you don't have right to left, you don't have spans, it is only one line, you are not going to do anything fancy. If it is the case, boring layout dot is boring is going to return to you metrics. You can use this metric object to call boring layout dot make as a boring argument, of course, and make it draw, make it compute layout for you. There are many parameters, but most of the time you don't really have to think about them because you want a normal alignment of text, you want a normal space between each character and each line, you want to truncate the text at its end. It's very classical. So in fact, you can't, well, if you want to write optimized code, you can't just call boring layout.make. You need to also keep boring layout instance. That way, you can call on this instance replace or make. It is simply a case of not allocating a new text.layout if it is possible. When it is done, okay, we have a boring layout. And if it is not boring, so if it is multi-line, if we have a span, if it's complex, we can't use a boring layout. It is not going to work. Instead, we need to use static layout. It is mostly the same logic. The constructor is even more horrible. So there are many parameters. And in fact, you even need to use a reflection to access to the most important constructor because it is hidden in most versions of Android. It is quite safe, however, and quite speedy as well, since you only need to use reflection to fetch the constructor once, not for each call. And if you are targeting Marshmallow, the platform finally provides a builder for static layout. So, it's quite a call. Creating a text layout is often quite complex. But once I have computed if it's boring or not, and created a layout, I am ready to draw. And in fact, it is not complicated at all. First, I just want to check if I need to draw something, because well, if it is empty, I have no time to lose. Then I just save the canvas position. I clip it to the bounds I want to apply to the text layout, so it's just the place in the canvas where I want to draw. I translate again just to get to the right position where I want to draw, and I call layout.draw, a framework method that will draw the text for me. Finally, I just restore the canvas to its original position, so the draw path can continue. Okay, I have drawn text. Why would I want to do that? So the first advantage, just like with a custom view group, is that you've got absolute control over the drawing logic. So in some cases, you are going to try to do things that are not quite possible to do with the platform, even with something like spans. And if you use a custom draw logic, you can push the bounds of the platform way farther. And another big advantage is in terms of performances. Since we are writing the layout logic, we can, in this very specific case, use multi-threading. So most of all of the UI logic needs to happen on the UI thread, but if I compute layout on a worker thread in a secondary canvas during an idle phase of my scrolling, for example, I can just feed it during the layout and draw phases without costing it anything in terms of performances, in just a worker thread. And finally, with these two techniques, I have very good chances to have as much performances as I can get with most devices. Again, it's not something you want to do for any view. You need to be sure to measure your performances first and decide whether it's worth optimizing or not. But you can attain reasonable performances on Android, even for complicated tasks like scrolling, which is very often junky on Android. Finally, if you are interested in this kind of complex UI problems, or if you want to build an audio engine, Deezer is currently hiring, so we have a booth in the main hall, so come discuss with us. Do you have any questions?
Very simple question. How much faster is it? Did you measure the performance gains?
Sorry,
how much faster? Like 30%?
Ah, so it's a bit tricky because you don't really care whether your layout code run 10 or 100 times faster. Generally, you can get one order of magnitude. What you really care about is whether you are able to fit in a 16 millisecond budget. Because that's what, at the end of the day, really matters. That's the only real metric. In most cases, it really depends, of course, of what you are trying to display. If you want to display 1,000 views at the same time, it's not going to work, whatever you do. But if you got reasonable layouts, you can get on everything from Moto G or Android One device acceptable scrolling performances. In order to measure it more precisely, you can use the FrameStat command via ADB. It will give you a report on the scrolling frames and how many you are missing. And that way you can compare before and after. And even after you have written a custom view group, you can check whether new developments are killing performances or if it is still okay.
Thank you. Just one question. I thought the UI framework was only available to the UI thread. So if you do multi-thread to improve the code, so it means you're going to have to handle the synchronization of the different threads. And is it not the risk to actually miss the frame?
Yeah, it's of course it's a bit tricky. You need to be able to check. Again, with all the performance optimization, you need to identify the problem and try a potential solution and measure does it work or not. Usually, if you got draw text that is costly enough to make your scroll junky, it is worth computing the layout on another thread and synchronizing.
Thank you.